Boom. Alrighty. So today's question is, how do we evaluate limits analytically? So our goal today is finding limits analytically, 1.3. So we're learning to evaluate limits analytically. We'll be successful when we can evaluate limits analytically using a variety of strategies. So we already kind of talked about like how limit notation looks a little bit, but I just want to pull back some of the stuff that we did in pre-calc, looking at our math notes from pre-calc, like a definitional limit. And we kind of looked at this already and it's been in the reading. But given a function f and a fixed number a, there exists a unique value L such that as x approaches a, either from the left or the right, f of x approaches L. It's written like that. Again, the limit can be determined by checking out if the left-hand limit and the right-hand limit both agree and exist. So we kind of already know that. We've been spending some time on that. Our next lesson is specifically looking at left and right hand limits. So just so you know that when we get to 1.4, we'll specifically be focusing on that, but we'll also be looking at continuity quite a bit. So just FYI. Again, how that's read, I think this is redundant, but I just want to keep putting it in there because it's something that I want to make sure that we're still pretty good on. And I try to color code stuff just to remind you what the different pieces mean. The limit as x approaches c for the function sine of x is sine of c. Just pointing out some of the things about limit notation. Nothing like wild or crazy, nothing terribly new, but again, just to point it out because it's a thing that I want to mention. So you can write these down on your own or not, whatever. I'm just kind of pointing them out. There's some generalized thoughts and ideas. These are all in your book. But basically the idea here is that these are just some basic rules when it comes to limits. The one that's really particularly helpful, I think, is this, let me get my pointer out, is this very last one down here. These other ones are helpful for lots of different reasons, but this one helps us out with a lot of different things, trying to determine some limits that maybe we don't know. So that's something that's kind of helpful. But these are just different properties of limits that you should know exist. And it's not like they don't make sense. Like a lot of these I feel like are intuitive. Like, well, yeah, of course that makes sense. You multiply, like you stretch a function, multiply each output by a value, that should happen. Now, a note about everything that's going on here. C, D, and L are all constants, and f of x and g of x are continuous functions. Continuous functions. And for us, continuous functions, like we'll delve into that more later, but basically the limit and the function agree at every point on its domain. On the open interval, negative infinity, or just on the open interval of its defined domain. And that'll make more sense when we look at that later. And just kind of looking at those different things. Remember, this is a plus or minus symbol, which means that if you do f of x plus g of x, that would be f of c plus g of c. Or if it's f of x minus g of x, it'd be f of c minus g of c. The reason we use that notation is so I don't have to write two different lines of stuff. We used the plus or minus in pre-calc when we did the angle identities. Because for something like for cosine, the sign is flipped. Because the one was cosine of a plus or minus b, in the middle was a minus plus. So it was opposite of whatever you started with. So the plus minus is the most common one. Minus plus only shows up when there's a opposite association. But those are basic limit rules. Again, they're in the book. I'm spending way more time on them than they really need to be addressed, but there's something you should know and I want to make sure I pointed them out. These are all, the only two of these that are really interesting are the bottom two. Because if you have a continuous function, which if it's continuous on an interval, the limit should exist as well. And that's why I point out with all 6 trig functions is that with sine, cosine, tangent, cosecant, secant, cotangent, where it's continuous, the limit exists. Now, with 4 of those, cosecant, secant, tangent, and cotangent, they have spots where they're not continuous because they have vertical asymptotes. So at those spots, I mean, the limit doesn't equal a particular value at that spot because it just doesn't exist. And they usually approach infinity from different ways. Sometimes they approach positive or negative infinity. So it's not really helpful to even say that otherwise. Those bottom 2 limits down there, we briefly looked at those in chapter 7 in pre-calc, right in the middle of it. We also used those a little bit at the end of the year when we were attempting to derive limits, derive derivatives of sine and cosine, which we'll look at derivatives in chapter 2, depending on how we decide to finish going through our book and such. But the proof of each of those is in the book. You'll need those limits for the practice that you're going to be working on tonight. So just make a note of them. You don't need to know why they work, but if you want to know why they work, and so it's not like I'm just, hey, here's a rule, because we've trained you to not just like, okay, here's the thing, use it. You generally want to know why it is and what it is. So there's that. I just wanted to check to make sure. Okay. So there's that. All right. So let's get on to the actual meat. So in the last section, with numeric and graphical approximations limits, the big thing with that is that we were approximating the limits. And to the best of our knowledge, that's what the limit was. But that's not always the case. Numerically, like from a table of values that you either create or look at, only gives you an estimate of what you think it should be. That isn't what the limit is. You just get an estimate. But if you want to exactly know what the limit is, you need to approach it analytically. And analytically just means we're using algebra. The techniques we're going to use are things we used last year. And some of them came up in chapter 13 right near the end of the year, so you might not remember them as well. But they were there, but we didn't spend tons of time talking about them because we didn't do we didn't do any synchronous stuff. The only synchronous stuff I did was answering questions on the fly. Just because I didn't know what to set up or how to set up and what I wanted to do, and we were just trying to get it through. And every week it was like, maybe we're coming back, and then maybe not, whatever. Anyways, I want to look at 2 different techniques for analytically determining the limits. So right now, with both of these, if you plugged in the first one, if you plugged in 0 to try to just evaluate it, you get 1 minus 1 over 0, which is 0 over 0. Indeterminate, dun dun dun, which means we need to try to do something else to determine what that limit is. So, and if you look over at the second limit, if you plug in 5, you get 0 over 0, dun dun dun, indeterminate again. So I'm going to go through rationalizing and factoring. And the tip off, other than the way I set them up, for rationalizing, generally, if there's a radical, you're going to try to rationalize it to make the limit a little bit easier to work with. And if you see different powers, like a disparity of powers, like there is over in the second one, how you have a linear term on the top and a quadratic term on the bottom, it might be a good time to factor. All right, so let's take a look. For this first one, to rationalize that, I need to multiply by its conjugate. So I'm going to multiply by the conjugate of this radical piece. So the conjugate is this radical piece made up of 2 parts, the radical and this part over here. The whole idea of the conjugate is that an expression with its conjugate, when they multiply together, should be differences of squares, and that's what's useful about that. So if I multiply by its conjugate, multiplying top and the bottom of my conjugate, because this is a giant 1. It doesn't change the value of what this is going to be. And if you think back to those limit rules, if I multiply this limit, it's just the same limit now, because this is technically 1. But it's going to allow us to do some more things. So now we've multiplied by the conjugate. Again, this is a difference of squares. So it's just going to be this squared minus this squared. Now I didn't multiply out the bottom, partially because I know what was coming, but also just because why do more work than necessary for a lot of things. One of our mantras in calculus is try not to multiply things out unless things aren't working out. Then multiply things out and see what happens. So in this case, hey, I can simplify the top a little bit. And yet again, I can do some simplifying. There's right there. Those x's can simplify. Now that I've taken care of those x's, let's try plugging in 0. Because ostensibly in step 2 and step 3, or in step 2 and step 3, nothing was really different. Like if we plugged in 0, we'd still get 0 over 0. But now, since we factored out those x's, simplify them away as 1s, maybe we'll get something different. So if I plug in 0, I get 1 over square root of 1 plus 1. So I get 1/2. So this limit is exactly 1/2. Again, this one in particular, when you have an equation, graphically and numerically, you can do some decent approximations, but sometimes it won't come out as nicely as 1/2. I know some of the answers to some of the problems we assign you are like square root of 2 or square root of 3 over 5 or something like that. So you want to make sure you are doing it analytically, showing the work as you go through it to try it out. All right, so that's rationalizing. Again, typically when there's a radical, we can do that. Sometimes when there's a radical, depending how it's set up, you can still do factoring. Sometimes it's just not always as obvious how that's going to work. So let's do this other one. Let's try factoring this second one. Well, I see this that looks like a difference of squares. And it in fact is. Since the difference of squares, I'm looking at those. I'm like, oh, look, there's a giant 1 I can simplify out. So I get 1 over x plus 5. I can plug in 5 now without it going to 0 over 0. Boom, 1/10. Those are our general techniques for analytically finding a limit. And if it's not one of those two things, generally it's just multiplying things out and seeing what simplifies and get rid of a giant 1 at some point. Notice we got rid of a giant 1 in both of these. And at some level, we exploited difference of squares to make this work for us. So you're going to see some more things in the practice that mirror a lot of this. But that's basically all I have for you. I have a couple things. Just pointing it out. Analytic is your algebraic approach. That's exactly finding the limits. Okay? Graphical and numerical, again, it's giving you an approximation. It's giving you an idea. I keep really trying to hit this hard because there was a couple questions that we looked at that we practiced from the AP Classroom, which if you haven't signed up for that yet, you need to go do that. That's part of your assignment today. If you haven't signed up for AP Classroom for this class, go to Schoology. There's directions in the code in Schoology for how to sign up. So make sure you do that today. And I'm going to end the meeting a little early unless people have questions, so that you have some time to just go do that. But anyways, what I was trying to say was there's a couple questions that AP likes to use where they give you a table and it looks like it's going to a value of, I don't know, 5.7. But the actual answer is the limit. We don't know. The limit might not exist because no matter how close we get from a numerical table, it gives us an idea. Without either an equation or a graph to kind of help us along and get an idea, we don't know. And even then with the graph, maybe the equation for the graph has a super, super small, like piecewise function that like within a millionth on either side of the value, something else happens. it's super troll, but or super troll-like to do something like that. But AP's not above that when they make these questions, because they want to make sure that if they can be as troll-like as possible in creating some of these questions, and you know they're going to be troll-like, you're going to be a lot more thoughtful and careful about what you do as you approach things. So that's why I'm pointing that out. And knowing what it's like to be a troll, I am also on your side and I can help you out with trolliness. So there's your analytic, graphical, numerical. That's the big difference. The next time I see you, like today's Thursday, so I'll see you next week. We're going to do an activity where we spend some time doing more of this in class. But this is all I have for you today. So I think most of you have finished 1-1 and 1-2 and submitted those. I've graded 1-1. I'll probably start doing 1-2 later today. Yeah, probably later today or tomorrow, something like that. I don't know. Usually Fridays, my plan is Friday afternoon is my grading time, but if I only do that, I'm going to never be caught up. So we'll see. What questions do you have before I end the meeting? All right. So again, 2 reminders. This practice, get it done. Once you have it done, submit it on Schoology. A general thing, make sure you're showing work because answers are everywhere. I mean, these are all odd problems, so you have answers to all the odds in the back of your book. So unlike in pre-calc where you had all the answers to all the homework, you have answers to odds. Notice we almost always assign you only odds so you can check your answers as you're going through stuff. That's intentional. It's not like, well, I wonder what problems. Let's do these. They'll never figure them out. Ha! No, we intentionally do that. And that's why we provided all the answers in pre-calc so that you could check your work, you check your answers as you go. Sign up for AP Classroom. I haven't checked recently to see if everyone signed up, but I'm making sure I explicitly tell you. And since we're ending the meeting just a little early, you have a couple minutes to go sign up for an AP Classroom. Doesn't mean you have to sign up for the AP test right this second, but we're going to be doing things in AP Classroom throughout the year, and I need you to be signed up for that so we can do those things. Like we'll be probably doing some assessments and assignments in AP Classroom, so I need you to sign up for that. After in the meeting, again, you can message me on Discord if you have particular questions and such, and some of you have been very prolific with that, and that's fabulous. Thank you. Again, you can also post questions in the AB public chat or the AP channel so that other folks in AB can get a benefit from your questions and thoughts and insights and such. That's all I got. So unless you have any other questions, I'm going to end recording and say, see you later.